Before the dawn of the computer era, it was hard to believe that hundreds of mathematical operations could be carried out in seconds. Of course, with the advent of computers, there's been a huge change in this perspective. The scientists and engineers of today are driven to find more and more computational power. This story is an old one.
First, we created computing devices to carry out tens of operations per second, then hundreds of operations per second, then thousands, and after thousands, millions, then billions, then trillions, and recently, quadrillions. Currently, computer engineers are looking to perform 1 quintillion operations per second. This amazing amount of computation is demanded by real problems in science, engineering, finance, and even entertainment. Engineers may now design on a computer instead of first designing on paper. These designs may be tested on a computer before any expensive prototype is built and tested in a lab. Scientists are now simulating phenomena that was previously impossible to be studied via experimentation. The evolution of the universe is a great example. You might think that trillions of computations in a second is excessive, but let me show you how trillions is in fact modest. Suppose we wish to make a prediction of the weather for each hour over the next 2 days. Further, we want our model to cover all of the United States and Canada from sea level to an altitude of 20 kilometers. A standard way to approach this is to cover the region of interest with a grid and then predict the weather at each grid point. So suppose we have a cubical grid and each cube is 100 meters on each side. The area of the United States and Canada is about 20 million square kilometers, and for the prescribed height, we need about 40 billion grid points. If it takes 100 calculations to determine the weather at a typical grid point, then, in order to predict the weather 1 hour from now, we will need about 40 trillion calculations. Except we want to do this each hour for the next 48 hours, making the total about 2 quadrillion calculations. Now, most computers have a clock speed of about 1 gigahertz. That is about 1 billion calculations per second. So, this whole process will take about 23 days. In other words, the situation is hopeless without more computational power. Imagine if we could perform 1 trillion calculations per second, then this problem would take a short 30 minutes. This may seem like a short amount of time, but in reality, we are getting the results we need by the skin of our teeth. So how do we build a classical computer which can compute 1 trillion operations per second? It isn't easy. Suppose we wanted to execute the following code in 1 second. A conventional computer sequentially fetches the current x and y from memory into registers, then adds them and finally stores them. This means we would need to achieve 3 trillion copies between memory registers each second. Therefore, to build our fast conventional computer, we must build 3 trillion words of memory, typically laid out in a square grid. Suppose the grid has side length s and we put our CPU in the center. Suppose that data travels at the speed of light, and let's call r the maximum distance of a word of memory from the CPU. So r must be about 100,000th of a meter. Now the maximum distance from a memory location to the CPU is about half of s. So we have that r is half of s, or s is 2 100,000ths of a meter. So a typical row will contain nearly 2 million words, and a single word of memory will need to fit into a tenth of a billionth of a meter. This is pretty small. The diameter of a single small atom is about a billionth of a meter. Until we begin to represent 32 or 64-bit words with a single atom, we will find that these clock speeds are simply impossible to attain. Worse, it is not hard to imagine simple modifications of this problem so that trillions of operations are no longer sufficient. For example, suppose we wanted to do a whole Earth weather simulation. Then the area increases by a factor of 25 from 20 million square kilometers to 500 million square kilometers, and instead of taking 30 minutes, the whole process will now take about 13 hours. This makes our first 12 predictions useless. Further, other problems require even more computational power. We currently cannot create detailed atomic-level simulations of biological molecules. There are numerous other simulations that would expedite the design and manufacture of integrated circuits, but they require vastly greater computational power than we currently possess. So how do we build this machine? Let's consider an analogous problem. Peter is a Roman contractor who specializes in excavation. His single laborer, Paul, excavates 1,000 cubic feet per day. Imagine the problem when it's reported that Attila the Hun is going to visit Rome next week. Peter determines that he will need to excavate 100,000 cubic feet a day for the next week. Peter's no fool. He simply hires 99 more men, and now they can meet demand. And so with computing, our single worker is the computer processor and its memory. Our 100,000 cubic feet per day is the next computationally demanding problem. The bad news is that even though we know in theory how to obtain virtually unlimited computational power, we are not always sure how to use it. We have not yet said how our processes work together. By analogy, for Peter, it is easy to use his resources. He gives each worker a shovel and tells them to dig. In other words, his processors do not need to communicate with each other to do their jobs. Peter's problem is work-intensive, but not too difficult to coordinate. Now imagine if Peter and his men are instead tasked with rebuilding Rome after it is sacked by Attila. Peter now needs more than just unskilled workers. Specifically, he needs urban planners, architects, carpenters, masons, etc. And each of them need their own distinct set of resources. And worse, each worker needs to coordinate with each other. Of course, the analogous situation for processors is much more complicated. A better analogy would be if Peter, instead of hiring urban planners and architects and so on, hired a large number of workers, each ignorant of the work they had to carry out, and Peter had to individually instruct each of the men in the appropriate art. In this course, Rome is a computational problem, and you are Peter. It will be up to you to ensure that each processor gets the appropriate instructions and data to perform its calculations.